do just as well because you can, by construction, you create a model that's deeper, but performs at least the same way as a shallower model. So lots and lots of attempts at trying to figure out how to do this. But basically, this little connection right here that we're going to call a skip connection, does the trick. So in a typical neural network, you would just have, like your convolutional layer followed by, activation. We learned about batch normalization. Oh, I forgot. We were supposed to finish up the batch normalization. We'll do that at the end. My bad. Have a normalization layer in there, but basically, convolutional layer, nonlinear activation, convolutional layer, and what the ResNet adds in this in what's known as a residual block, this whole thing being thought as a block, is to kind of just change the problem a little bit. So where does this word residual come from? Well, you still have your convolution, activation, convolution, but instead of trying to learn, say like the function h from the input here to here, what you do is you just take your input and you just basically add it back into whatever the output is here. So instead of needing to learn this like the whole input h, you basically like turn it into, h is actually equal to whatever your input was plus some like change to that input. So this is known as the residual. What's the difference between, like, what has this done to our input? Well, what it's done is f. When you add this in here, what you're having the network learn here between the input and the output here is just like basically the difference, like the change that's being made to the input. And as a result, this becomes like a really powerful way of allowing there to be to propagate signal backwards. Can you see why? Can you look at this? Think about the computational graph here, and think about like gradients. And can you see why this might solve, say, like the vanishing gradient problem?
Yeah, it's almost like we're short-circuiting this neural network.
Yeah, but how? That's true. But like how? Where are we like preserving gradient signal?
In the identity X.
Yeah, like what's happening there? When you backpropagate along there, like what's happening?
Almost all the convolution layers will see the loss function all the way down, and the X on the way up.
Yes. Yeah. So, and say it again, Kristen.
The derivative is always 1.
Okay.
Of the identity, so it's not going to vanish.
Right.
Because it's never.
Yep.
Yeah.
Yep. So that's exactly right. So you basically are going to have, as you propagate this signal back this way, you're going to have whatever's happening here, right? And like this could be a whole bunch of different things. Who knows? But it's it's the difference here. So like it actually might even be smaller, say, than here. But you are always making sure that you have like basically one branch of the back propagation, like along this computation graph, where, like it was pointed out, that the gradient along here is just a 1. So think about that in terms of like eigenvalues. Like as you multiply this together, right? Like every time you multiply a matrix with itself, you can kind of think of it, as operating along its eigen vector dimensions in space. And if the eigenvalue is 1, that it's just you're not changing the size of it. It's just it's not getting bigger, it's not getting smaller. It's just staying at 1. If those eigenvalues end up being smaller and you multiply them over and over, again, then those will start to get a lot smaller. You have the vanishing gradient problem. If it's greater than 1, they're going to start to explode. You have the exploding gradient problem. But in this case, like you're basically you're always preserving something at the kind of natural size of the signal all the way back to here. So, so even though like this H is more or less equivalent to F plus X, in the way that we do backpropagation, this just ensures that like nothing too crazy happens here. Like we always have a way of backpropagating some signal back. Where here, like these two things, like in some sense, these could diverge quite a bit from each other about what's learned. Like this has to do with like really how much capacity there is in a couple of layers like this. And like computationally, they can end up being really different, even if like analytically they're equivalent. And so from an optimization perspective, you just made it so that with like essentially the same kind of expressivity, you're ensuring that you're going to get some signal back to the earlier layers.
Well, don't the ReLUs act almost like a filter when you're in the zero part, which just flats out the signal completely?
I mean, it does do that, but like that's equivalent to here, right?
Yeah.
So like, if that's happening here, then it's also happening here.
So we fix it by making like a weakly ReLU instead of just a regular ReLU, so we get a little bit more gradient signal going back.
Yeah, but that's not really the issue of like why this is not back propagating. It's that it could happen that most of your signal is what could happen. So yeah, it's not. It doesn't have to do with the activation, like possibly setting like a lot of things to zero. I mean, equivalently, it could be setting a lot of things to zero over there, as well. But it just has to do with the fact that what I may learn in this set of layers, being kind of trained in this, like with the signal coming from here, may be quite different than when I learn from this here, even though analytically they're the same, right? It's just literally like in the optimization, like the way that we train these things, I've ensured that there's always going to be this signal here, no matter what. Regardless of you can change these. You're right. You can change to be a leaky ReLU, but like the same would apply. That you still have like this branch in the backpropagation that you don't have here. So it's just rephrasing the problem here, and as we do the optimization, makes it so that we're preserving gradient signal. So that's cool. It's cool because it's simple. It's cool because there's like not a whole lot that really has to change in our networks. Like it's you just have these connections. By the way, why does this connection go around two conv layers instead of like one here? Like why don't I just like remove this ReLU and this conv here and just kind of go around it like that and then apply ReLU?
Well, if you go before the first ReLU, then it's just like a linear combination.
That's exactly right. Yeah, that's exactly right. You just have it would just be a linear function, and so there'd be no advantage in the identity because it would be because this is linear. You could have already it's what I'm trying to say. You could already factored it out into like an identity and the appropriate matrix. But when you do this, you ensure that this is a nonlinear function, this f here, and so that there's like complexity being learned in this block. There's like a nonlinear complexity being learned in this block, so that this signal here is just not some like linear transformation of the signal that's in here.
So could we put it before the second conv?
Yeah. Mm-hmm. You could do that, but that ReLU, remember, is so much like an identity already. I mean, I don't have the zero part to it, but it's so close to an identity that like there's a lot to gain by adding the additional conv layer here. I'm sure that was tried. When they were putting these ideas together.
2 conv layers or 3.
Why not? Why do we do anything in neural networks? Because This is like the simplest, you know, kind of like Occam's razor. Like this is like the simplest kind of new idea that doesn't get, you know, too crazy. And you'll see here, we're actually going to expand on this idea in just a second on a residual block. But anyways, the point here is just this simple rethinking of how to learn the nonlinearity in a couple of conv layers really allows you to propagate signal back. Right. Okay, so what's the full architecture look like? Well, it has a whole bunch of these blocks. Except for at the very beginning, there's, like I said, I think I have this little slide. At the very beginning, there's a 7x7 convolution stride 2. Is that even on there? Yeah. So it looks like this. So input, you do this first fairly large convolution, 7x7 filter. Stride 2, so it's already going to, you know, reduce the size of the image. Then you have a cooling layer, and then you go into these blocks. And if you I don't know how well you can see it. It does say it over here, but you see that these are different colors. Like there's a bunch of these red ones, and purple ones, and yellow ones. And so these are like, so each one of these is like a residual block, and then these blocks are put into stages. And so what you can see is, in like the typical, you know, architecture, your first stage has a bunch of these residual, like 3x3 residual blocks with 64 filters. And then what happens every once in a while, you go to like a new stage. And again, it's just 3x3 residual blocks. But you see, what we did is we doubled the number of filters here. We went from 64 to 128. But at the same time, when we entered this new stage, just this first convolutional layer here did a stride 2. So it increased the number, it doubled the number of filters, but it also reduced the feature map size, the spatial extent by a factor of 2, 4 on both sides, when you put both sides together. But so what's happening is like you're trading off, you know, the spatial extent of the feature maps for additional filters. That's a way of kind of like balancing the computation, like the amount of like computation going into each one of these stages. And then, you know, you just kind of keep doing this. You know, each stage you would double the number of filters while, you know, when you enter it, having a convolution to stride 2. So it has that same kind of feel as a lot of these other networks, where instead of using pooling like throughout the network to reduce the spatial extent of the feature maps, it only uses this once here and just uses striding to do that reduction. Question, yeah.
So these lines coming around each block, is this the adding identity thing?
Yep, exactly. Yeah. Oh, yeah. If it's not clear, I'm glad you asked that. Yeah. Each one of these has a residual block, so it looks like this. And that's what that thing is going around, right? It's meant to show, you know, that's why it's 2 layers, right? This is one of these right here, and this is one of the others, and so forth.
So it's assumed it's happening every single time.
Every single time. Yep. Every single time. So, like in some sense, the architecture is quite, even though it's deep, it's quite simple, right? It's a bunch of these blocks. All you got to do is, you know, there's always 3x3 convolutions. All you got to do is keep track of the filters and the just when you change stages that you're going to do a stride 2 convolution.
So like as you change color, the first convolution is like a stride 2. And sorry if this is obvious, but I'm not sure. Is there like a fixed stride for the next one?
Yeah, everything else would be stride 1. Yep. So it's like, I think I might have this in the next couple slides, but it's like, you know, I'm reducing the spatial extent of the feature maps. Then they stay the same for a while, and then I get here, reducing to go into here, and they stay the same through purple. Then I reduce it at some point again. They get smaller. They stay the same through the next color, and so forth until you get to the end. Yep. No, it's a great question to clarify that.
So instead of doing a max pull, you just increase the stride by 1?
Yep, just do a stride 2. Yep, to reduce the spatial extent. just as you enter like the what's called a stage. And then, of course, we've got to we're doing classification, so at some point we have to turn this into a vector of length 1000, because those are going to be our scores that go into softmax and then go into the cross-entropy loss. So the way that this works is that there's a pooling layer at the end of all of this, but it's a global average pooling, which means you take your feature map, and at this point you have in this example you'd have 512. So whatever it is, it's going to be k by k by 512. So what you do is each one of those channels, you just the k by k entries, you just average those all. That gives you a vector of length 512. You have one fully connected layer to turn that into a vector of length 1000, and then that's input to the softmax and then to your cross-entropy loss.
So you're deciding between 1,000 different classes based on only 512 features. In that case.
In this case, the answer is yes. Yeah. When this is actually we're about to say it, but this is actually for the shallower versions of ResNet. The larger, the deeper ones actually end up having a lot more filters. But yeah, you're exactly right. And really, you should be able, with 512 features, you should be able to learn way more than 1,000 classes, because they work together to.
But you can have an
define
exclusive OR feature since it's just one fully connected layer.
What's that?
You can't have ears and a nose or an ear kind of.
Yeah, but it doesn't work that way. The features aren't that interpretable, right? So they really, after you do things like things like dropout and whatever, you have a very dense representation of the image, and there's no one unit really that said is your ears and things like that. I mean, we kind of hope to interpret it that way, but it doesn't really in practice work out that way. They're far more abstract notions, and then they all feed into what does it mean to be a cat or to a dog or whatever. And actually, in ImageNet, there's dozens and dozens of dog species, so things are good about it. Okay, so these things can be if you go again to your model zoo, you're going to see that you have choices of usually there's actually a ResNet 18. It's not on here, but ResNet 18, a ResNet 34, a ResNet 50, a ResNet 101, and a ResNet 152. And sometimes there's a ResNet, 1,000. Can't remember what it is, but 1,000 layers. If you look at the paper, they did some studies where they even had 1,000 layers, but there didn't seem to be much benefit in terms of the competition over 152 layers. But as you get deeper, remember that there's tons and tons of operations happening within each one of these blocks. And remember how in Inception, it was kind of the same story where there was a desire to to reduce the amount of computation per block, we introduced the idea of using one-by-one convolutions to do a bottleneck, and the same thing happens here. So what happens now is you get this. So when the networks get deeper, so it's 18, 34, these ones use just the regular blocks, and you'll see this if you look through the code in any model zoo. But when it gets to 50, now the blocks turn into these bottleneck blocks. So what does that mean? Well, here's an example. Let's say we're currently the current input feature map is a 28 by 20 by 256. What we typically do is we use one-by-one convolutions to go to a fourth of the number of filters. So that's why you're going 256 to 64 here, because 64 is a fourth of 256. And then we do the 3 by 3 convolution. And then we use one-by-ones to go back to however many filters we had, in this case 256. And then we skip around all of that. So this is the typical, so in these deeper networks, like the ones that won the competition, you would see these residual blocks. And yeah, so when we do this, for example, in this particular in this particular example, you'd see, yeah, I just told you all this. Oops, sorry. But the point is that like the total number of operations being done in here is drastically reduced because you've reduced the number of filters before you do the 3x3 convolution. Okay. Yeah. Question?
So I remember before there were 2 layers of 3x3, right?
Yep. Now it's 1x1, 3x3, and then back to 1x1. Yeah. So it's different in that way. Yep. But then you just have a whole bunch of these.
Thank you.
But you have 3 layers now. This is kind of going back to something that Anthony said. Why not 3? Well, no, you do have 3, but they're not all 3x3 convolutions.
Where's the ReLU in this?
They're in there. There's always a ReLU in flag in between each one. Yeah.
When do we know like we are using too many filters? Like till what number should we scale up to? Like in that case, we were like going to 2 to the power 9, like a 512. So like so how many? So what is the optimal basically maximum filter we could reach? Or
There's no. I mean, hopefully that's one of the things that you will also kind of understand about deep learning here. There's no way of saying what is the optimal number of features. It depends on the data set for one, and it also depends on your hardware. Like, can you do more filters? Like, you may not be able to. Like, it would, like in the end, it would be better if these just stayed like the 3x3, like regular residual blocks. Like you had 2 3x3 convolutions. Like it's more expressive. But the point is that with the amount of memory you have, you couldn't like the feature maps start getting too big in terms of amount of memory, so you can't do that. So the amount of memory required to do the operation. So you can't do that. So like these are ways of kind of getting around that while still maintaining the depth. So it's just like there's a couple of constraints you have. Your amount of compute, like the data set itself, both its size and like the distribution of it, like how complicated it is to learn, so to speak. And you basically, like with ResNets, you kind of have this formula where you basically are deciding like how many layers, like how many stages, and then you just kind of follow this formula of, usually like starting with 64, and then every time you move to a new stage, doubling the number of filters. And you have to also make a decision about like how many of these blocks are going to be in each stage, and it's different. Like as it gets deeper, like it's different. Like you look at the paper, you see like what they did is just there doesn't seem to be too much kind of rhyme or reason about how many residual blocks went into each stage. It just was sort of like what fit, and like after running training a bunch of these things on that data set, like seeing what gave the best results. So again, a priori you really couldn't say. You're just trying to like get a really deep expressive network to train.
So how do we like make sure like our feature maps aren't just learning the same thing or not learning anything at all? Could we like check if any of the 2 of them are too similar and we drop one of them out? And
this is what's really cool about ResNets is that you have like a really explicit way of seeing like if you need the depth, because you can look and see, because you always have these identities, what you can look and see is like, is there anything like useful happening here, right? Like these could end up being identities, right? Like you're looking at the difference, like this is really like the difference of the signal that you're trying to learn from the input. And so it's really the case that you can go look at those filters and find out that they're just like, so said differently, like in ResNets, it's very often the case that you would train a really big network on maybe not so much data or like complicated data, and like because it's propagating the signal through, instead of it just kind of like not learning anything, it just learns to kind of have a whole bunch of blocks that are just identity. Like basically, like the operation here is just a 0. Like these don't do anything, and it's just the skip connection that's doing the trick. So like the whole block itself is just the identity. Those filters are like zeros essentially. So yeah, it's like pretty easy to check into that. Cool. So ResNets in 2015. when they were doing this with the competition, they used batch normalization after every conv layer. They used something like the Xavier initialization that we saw earlier, but there's a small change to it that actually accounts for ReLUs. It's trained with stochastic gradient descent and with momentum, and the parameter for momentum is just 0.9, a very, very typical choice. Loading rate starts at 0.1, is divided by 10 every time. Again, the validation error would plateau. Batch size is of 256. There was a L2 regularization, often called weight decay, 10 to the minus 5, and there was no dropout used at all here, which is cool. So what does this look like? This Xavier 2. So remember this picture we looked at last time? We kind of justified this formula up here for how to randomly initialize your weights. And there was a question about, like, well, what about ReLUs? Because ReLUs aren't just these nice Gaussians. And it was like, well, they did all this math to kind of justify it for, like, in this linear activation case, and this saw that, like, hey, it basically worked when we did ReLUs. But now that we're training much deeper networks, turns out it wasn't such a great initialization. Like, there were some problems with it when it came to ReLUs. So, in fact, the ReLU story looks a little bit like this, right? So ReLUs are going to have, set a bunch of things to 0, this kind of spike at 0, and then have some distribution of positive things. But if you use that kind of naive Xavier initialization, you tend to see again that, like, all of these activations are starting to converge to 0. Like, something like we're losing signal down the network. So for a little bit of additional kind of thinking about this for ReLUs, this was decided to be like the right way to do this. So in order to kind of preserve the dynamic range of the original distribution of the ReLUs. And instead of it being now you divide by this, so it was divide by the square root of fan in. Now it's divided by the square root of 2 over fan in. So like the size of the input going into the layer. And again, there's a bit of mathematical justification for it. Here's using that same experiment. Seeing that the distributions are actually preserved as you at this random weight initialization as you move through the forward pass of the network, and that's what was used. So yeah, here you go. That's the initialization that was used here. So again, this was driven because of like the additional depth, and that they were basically trying to solve this problem of being able to train really deep networks. Yeah, this is something about the error rate. Another empirical study showing the error rates tend to decrease rapidly with the number of times you pass over the data. So cool. So again, I already mentioned this. It won everything. There's like some statement about all the other competitions. So the classification problem, the detection problem, localization problem. These are kinds of computer vision tasks that we'll talk about next week. Detection and segmentation in COCO, which is a totally different data set and totally different competition. Won them all. So resonance all of a sudden were like all the rage in 2015. And as we already pointed out, better than human performance. Okay, so we're going to do a little bit of like thinking about some of the networks that we've looked at before. This is a kind of a cool kind of meta-analysis done in 2017 of a bunch of different kinds of networks, some of which we've learned about, some of which we haven't, but we've learned something about them. So what it's showing you here is how well the network does on the ImageNet competition data. This is now reporting top 1 accuracy instead of top 5 % accuracy, and what you see here is, starting with AlexNet over here, you're seeing your GoogleNet, your VGGs. You start to see some ResNet. You're seeing, the increase in the ability to do well on this task, right? So as we go from left to right, we're getting better and better and better. So like the earlier winners of the competition, kind of early on here, some increase, but not doing as well as the ResNets. The most shallow ResNet actually doing worse than these VGGs. Not too much worse, just by a couple of percentage points here. But then you start to see this rapid increase as you increase the depth of the ResNets until you get to 152, and you can see it's about the same as 101 here. Again, on the top one accuracy, so it's a little bit different from numbers that we've been looking at. But then you see these inception V3 and V4. So the group that was behind GoogleNet kept iterating on inception and adding like new features and like new capabilities, and actually started combining them with things like ResNet. In fact, this V4, Inception V4 is like ResNet plus Inception. So like you add residual connections into the Inception modules and allows you to have like many more Inception modules. And notice how it does better than them all. And the reason for that is that you're able to backpropagate signal better. And remember, Inception has like all this kind of multi-scale thing happening, and so you're just getting a richer representation of the data, of the features, and you're just able to learn a lot more. So what's interesting is to look at this and to look at this next plot over here, which is showing again like three different things. So again, like the top one accuracy. So like the level of these models kind of matches the level over here. But you're seeing a couple other things. You're seeing the number of operations needed in like a forward pass, and then you're also seeing some representation through the size of the circle here about the number of parameters that these models have. So what stands out here? When you look at that, like what things stand out?
The operations are going down.
Right, like going down from like something over here. So the first thing that should stand out here is BGGs are just like hogs, right? Like they're huge. They have a huge number of parameters. They require a large number of operations, and they're not nearly as good as some of the other networks that are on here now. So that's like the first thing that should stand out. Next thing is like just looking at AlexNet. This is AlexNet with batch norm. So like these things don't do well. They're just not deep, right? So they just don't have a chance to learn a whole lot of interesting features. Then you have you have Inception, and then the other versions of Inception here. But importantly, these are tiny, right? Like these networks tend to do almost as well as we know as like the VGGs, but with far fewer parameters. And then the ResNets start to become, they're adding depth. So you see this nice increase as you go from ResNet 18 to 34 to 50 to 101 and 152. You see this nice. It is plateauing, but for not too many more feature or parameters, you're getting this really nice increase in the ability to do the task. And not too much increase either in the number of operations. But interestingly, these like combination Inception with ResNet, you're actually able to have a smaller network, fewer operations, but do better on the task. So it's not just all about like number of parameters, and even really like depth. There's like some, there's obviously depth matters a lot as you can see from this plot, but it has something to do with really like how is the network set up to really use the capacity that it has. And obviously the ResNets, do a really great job of taking advantage of those facts. The big jump from like Google Nets, like Inception v1 to like v3 and v4, I think is pretty interesting. Yeah. Sorry, I always talk through it and hear your slides.
Sorry, what is the radius of this disk represent?
The number of parameters. The key is right here. Sorry, I should have pointed that out. The key's right here. Just for time, we will look at that. Okay, so so improvements on ResNets. So a paper came out from the same group that did ResNets in 2015 called Identity Mappings and Deep Residual Networks. It was basically like they had spent a lot more time with ResNets and they made a few adjustments. So they improved the ResNet block design. So it didn't always look like this, but it's really where the batch norms go. So this is really quite interesting. Like we typically think of like the batch norms kind of following, like the convolutional layer or even the activation. But they basically in this paper were showing that if you make your block look like this, we're actually entering into it. You do a batch norm and then activation, this regular activation, and then your conv layer, and then do it again. That like this residual block pattern was best. You got better results with it. Seemed a little bit weird, at first, because you're thinking like, whoa, you're gonna do batch norm first. You're gonna do this kind of like standardization of the output first. But if you think about it, this is happening right after, like the input that's coming into here is, this addition of the input from the block before with whatever happened here. And so, it is in some sense, it is coming after the convolutional layer, but after you do the skip connection. So they just found that was better. Like that's like one of the main points of this paper is that. The other thing too is that remember that the ReLUs in the original blocks were happening like right after this. So now the ReLUs are like squarely within the residual block, and that had better performance as well. So anyways, not much of a change, but that actually gave better performance. People started playing around with these things a bunch. So if deep networks are doing well, why not make them deep and wide? And so basically, like people started playing around with just the same residual or ResNet architecture, but just having way more filters. That's what the wide part is. Just having tons and tons more filters, more than you could than you could fit maybe in previous architecture or previous hardware and things like that. If you do make these wide, you can't make them like for the same like compute or like the same like memory constraints. You can't have your networks be as deep if you're actually making them wider. And like the point of this paper was to show that like, well, what we really think is going on here is like it's the residual connection that matters, not necessarily like how deep it gets. So if you can make these, if you can make each one of these blocks like far more expressive, we think you can learn more. And through they basically showed that they could get the 50-layer wide ResNet like this to basically outperform the 152-layer like original ResNet. So wide ResNets are a thing. Again, you find these in most model zoos. This is not the combination of like Inception and ResNets, but it's something that kind of looks a little bit like it. So there were these things called ResNexts, which becomes hard to say. Same group from Microsoft that did the original ResNets. But what they do is like the blocks here, the residual blocks, instead of them being just looking like this, they now have multiple pathways through here. In fact, tons and tons and tons of them. And this, like a typical block might have 32 of these pass through here. You have far fewer filters in each one of these paths. And so that like you're not getting like a huge memory blow up. And then you're going to concatenate those all back together and then do like the residual connection, the skip connection, and that's your whole block. And that these tended to like, be able to learn. So yeah, so in general, like these tend to do a bit better than resonances. I don't know, like it's like totally accepted that these are like way better, but they have a bit of a different inductive bias. And again, you're having these like parallel pathways. So like at the same depth, you're having like different chances to kind of learn like less correlated filters within each block. So like this is one of the things that people were starting to see with resonance is that after a certain depth in the network, you were seeing like very correlated filters. Just there's like it's like harder and harder to learn like more and more abstract features, and like this was a way of kind of dealing with that. So they're called Resnex. So good to know about. Again, you'll find Resnex in pretty much all model zoos. Let's see how many other time. People start doing like really cool, funky things. So like, here's like an idea of dropout. So, in these stages, you always just have like the same number, like the same size feature maps. So when you have that, then you can start to play around with things like depth here. So this is like a dropout idea, but you would drop out like full blocks within the stage. And so now you're making like the things that you're learning like more robust within the blocks themselves, not just at the individual units. That's kind of interesting. I mean, you don't really see this being used much, but the way that the architecture is set up allows you to do kind of cool things like this, try things like this out. This is all kind of following on the 2015. What happened in 2016? What did the winner look like? Basically, the winner was just took all of these innovations that we were just looking at, and basically put them all together in like some big ensemble model. So Inception V3, Inception V4, Inception V2, but with like residual connections, a deep ResNet, the wide ResNet, put them all together, and voila, you get even better performance. So, somebody else did all the hard work in some sense of like creating all these, all these other architectures, and this group just won like them all together into an ensemble. In 2017, you get something new and quite a bit better performance. It's these SE nets, the squeeze and excitation. So they're kind of cool. What you have is it's a kind of architecture that could be added to anything. ResNets, Inception nets. The idea here is that you're going to learn a kind of reweighting of the feature maps before they go into like the next stage of your network. So the idea here is I have my feature map. In the picture here from the paper, it's like, and maybe it's best to look at it right here. So I got my feature map. It might be kind of arbitrarily H by W by C, right? Typically, like H and W are the same number, and C, C is the number of channels. But what I'm going to do is I'm going to kind of scale it so that the values here are like kind of on a similar scale. And then what I'm going to do is I'm going to learn like a weighting vector, but I'm then going to a vector the length of the number of channels. And then all I'm going to do is I'm going to take that output, I'm going to multiply each feature map by the corresponding value in this vector, and just kind of rescale it in the feature map. And so I basically have something that looks like the original feature map coming into this, but in a data dependent way. It's just going to kind of allow the channels to be rescaled against each other. And this actually adds a bunch more expressivity and allows you to get to this what was like 2.3 top 5 error rate. The base architecture that they used was this 152 layer res next. So like the one that we were just looking at, that has like the multiple paths in each block, but it was adding these to each one of the feature maps. So anyways, additional innovations there. And then basically at the end of 2017, people just said, you know what, this competition's like, we're done. Like this competition's like did what it set out to do. We've made huge strides in 8 years of competition from where we were to like doing superhuman having superhuman capability on these tasks, and so we're not going to have the competition anymore. But that doesn't stop the innovation in convolutional neural networks. And one very, very popular network that is like in the spirit of ResNets, but like kind of takes it to the next level in some sense, are these what are called dense nets. The paper's called densely connected convolutional networks, but the networks themselves are known as dense nets. And what you have now are these dense blocks. So so a little bit like ResNets, you have these skip connections, but basically you have skip connections like wherever you can possibly put them. So again, you're arranging these kind of blocks. You have your feature map input, then you have convolutional layer. There is going to be nonlinear activation here, just not showing it. And then you're going to instead of adding, you're going to concatenate the input with the output of this conv layer. Okay. So not adding, but just concatenating. So that means that this is not doing like a stride 2 or something. It's preserving the size of the feature map. How many filters there are here? You're going to just add it to the number of filters here, and you're going to have the same spatial extent feature map, but like with more filters. And then on that we do a convolutional layer, and again we're going to concatenate with that the input from the previous conv layer and the input from the conv layer previous to that, or in this case just the original input. So that's what these two arrows are showing here. Right. So in the first layer of this block, you're gonna concatenate this, but when you get to here, you're gonna concatenate both this and this together, and then you do it again when you go through another convolutional layer. This one's 1 by 1 because you can imagine it's starting to get pretty large in terms of the number of filters you have. You got to reduce the number of filters. But again, what I'm going to do is I'm going to take whatever the output is from here and concatenate the original output and the input and the output from the first layer, output from the second layer, and put it all concatenated here, and then do it again. And I just my dense network or my dense blocks are going to be you have again a choice of like how many conv layers and kind of like what the look would be of them, but it's it kind of has the spirit again of ResNet where you're like connecting the output, but you're just doing it like over and over, kind of in this recursive way. And these things are extremely powerful. Like these networks are extremely expressive in in the same depth as like ResNets, but as you can imagine, just this ability to kind of continuing to as you're concatenating these things, each one of these outputs is like not just like, if you think about it, not just like what happened before, but every time you run one of these convolutions, you're doing a 3 by 3 convolution here. You're sort of changing the scale on which the feature map, like you think about how we talk about receptive fields. Like you're kind of adding some, you're making the receptive fields a lot larger. So it's kind of changing the scale on which the features are working on. And so as you kind of do this over and over and over again, the input sort of becomes more and more multi-scale. And this ability to have this kind of multi-scale input at every one of these layers, this becomes a really expressive feature. So these become really, really, really powerful. And you see these used all the time. Again, so you're going to see dense nets of various depths in your model zoos. There's this thing called squeeze nets. What was their question?
Yeah, so what accuracy did those guys get?
On the ImageNet?
Yeah.
I don't. These weren't entered into the competition. This is like something afterwards. I'm not totally sure. I think if you look, like we were to go pull up, maybe we should do this after class. If we go pull the model zoo from like PyTorch or something like that, they typically have a performance on the ImageNet, and so we could look it up. But it's going to be 2% error rate.
So no one's gotten all the way to 0 yet?
No. Why is that? Do you know why? Because humans labeled the data set, and so they're not; those aren't perfect labels. So there's error in the labels. Yeah. People still kind of benchmark on the ImageNet, but they're not trying to go to like 0. It's kind of a fool's errand to try to go like that.
Well, in that case, wouldn't we be classifying how humans make errors in classifications?
Yeah, you'd be overfitting to human error, and that would be a bad thing, I guess, to be overfit to. And sometimes when you start to do this well, like you already are there, because if humans in general only get 5% of this wrong, you're already you could assume that the labels are wrong 5% of the time, and something along those lines, and you're already overfitting to it as you get to the 2s and 3% too. There's other things that you'll often see in model zoos, like a squeeze net. This is just putting 1x1 convolutions everywhere you can to make things really efficient, and when you're doing your convolutional layers. So really, I should add some slides here about things like mobile net, efficient net, which are other kind of ideas on how to make models that have good performance on something like the ImageNet task, but have far fewer parameters. And anyway, SqueezeNet's one of those. But you also see things like mobile net and efficient net in model zoos. I don't have any slides on those right now. And then you get to really interesting areas of research, like neural architecture search. So basically, this is something that there's a whole bunch of ideas in this area right here, but the basic idea here is to allow your network. So up to this point, we've basically made some, think of it as a hyperparameter choice of the architecture, and then we see how well that architecture does. We might tweak that a bunch and see what the best architecture is, but we're basically we're making the choices about the architecture. You can set up the learning in such a way, and you can kind of start to see how this might work when you think about the stochastic depth networks where you kind of drop out residual blocks. But you can basically allow things like the number of filters that you're learning, the size of those, to be learnable parameters, and you got to combine it with other ideas, ideas from reinforcement learning, which we haven't gotten to yet. But you can start to again, in an end-to-end way, learn the architecture as you learn the task, which is really cool. So the whole area is in this neural architecture search, and just kind of pointing out that it's out there. And probably one day will be the way that we maybe approach most models, but it's still to approach model choice, model selection, but it's still really expensive to run this. You basically need to spend a lot of time on GPUs finding the best architecture, as you might expect. It's basically just giving the networks the choice here of changing the architecture rather than the human looking at the results and making some decisions. These are just other ways of doing it. So I want to preserve a couple of minutes here to go back to the other slides and finish up the other two. I meant to do that. I forgot about it. But anyways, we talked about a lot of different kinds of architectures, most of which, like these ones, like ResNet and these ones down here, like people are using all the time today. Like if you go look at a calc competition right now, like who's winning in it, like in a computer vision one, you're gonna see ensembles of usually not even ResNets. You usually see something like ResNex or SE ResNex, which is using this idea with the ResNex. You'll see dense nets. You start to see a lot more like efficient nets now too. You don't typically see wide ResNets. Not really sure, but just not as typical. But even like today, 2021, these architectures are the typical backbones you would see in like state-of-the-art kind of performance on competitions. And then like in industry, you're going to see these too for computer vision. So if you listen to any like the recent talks that Andre Karpathy's giving about Tesla and how they're doing the training of their networks for the autopilot. I think I mentioned this last time. But basically, like there's a single computer vision backbone for kind of all the tasks that the car needs to do, and it's some version of a ResNet. I don't say exactly what it is. I don't blame them for not saying the details, but it's like some kind of ResNet, right? So, ResNets, at least for now, like the idea of the residual connection is like the key idea in computer vision, and basically everything else is something that employs that idea and allows you to have these much deeper networks. Okay, cool.
It almost seems like cheating that we're just gluing the output to almost every layer.
Not cheating, thank goodness. Let's see, let me hard to figure this out. Let's figure this out. No, I'm just going back to the other slides and just finish off. Yeah, here we go. Okay, so I didn't finish the discussion on batch norm. I meant to start here, but I forgot. Okay, so remember, batch norm was this really simple idea. You take the batch. At every place where you're doing this, you're taking the input, and for standard batch norm, you're going to do this channel by channel. You're going to divide by the mean, subtract the mean, divide by the standard deviation of within that channel, and then you're going to standardize. That's called standardization. And then you have these two parameters that allow you to learn, a way of scaling that. Divide. So basically, if this was normal data in the end, it would be mean 0, standard deviation of 1. Now this would be mean beta standard deviation of sigma, gamma. So, anyways, that's what it is. It works fantastically. It's a big part of being able to train deep networks as well, because you're not challenging each like ResNet block to learn like a distribution that's varying from like mini batch to mini batch. Okay, so importantly, we're estimating, not only are we learning these parameters gamma and beta, but we're also, we have this mean and this variance that we're learning at every batch. Or not, I shouldn't say we're learning, I apologize. That we're computing every batch. We're not learning it, we're computing it. So what happens at test time? What should we be doing at test time? Should that mean and that variance depend on the batch at test time? That seems actually kind of weird if you think about it, because you're now making the prediction dependent on whatever batch like that test example is in, and like that could be random. So that seems a little bit weird. So what you do at test time is instead during training you actually keep a running average of the mean and the variance here, right? So like you have all these mini batches, so you just have this this moving average, this exponential exponentially moving average of both the batch mean and the batch variances. And when you're done training, like the thought is that that's basically the mean and the variance of the entire data set. You can kind of argue that it is. I mean, it's not going to, it's an estimate of it anyway, it's a decent estimate. And it's easy to compute as well. You just kind of keep track of it as you go. And at test time, you then use those means and variances to when computing the batch normal layer, like the operation of the batch normal layer. So you don't make it dependent on whatever batch you sampled that test example in, but you make it dependent basically on the training data. So that's important, right? So simple standardization operation, you have two learned parameters, and then at test time, you actually use the these moving averages of the means and the variances from during training, and that just makes everything work really well. You can get kind of fancy with this. You could make sure that like your variance is whitened every single time. You don't usually see that, but you could. Hey, remember we were talking all about inception V2 and V3 through this whole thing, but we didn't talk about what they actually were. So this is what V2 and V3 are. So V2 adds batch normalization, and then V3 does this kind of, in each one of these modules, it does this kind of factoring of the filters. So this is what this was like a kind of a standard module. But what it does for efficiency, but again preserving the same receptive field, is instead of having like an n by n, remember the 3 by 3 and 5 by 5s, instead of doing that, what you would do is you'd use convolution filters that are 1 by n's of like 3 or 5, and then n by 1, so again 3 or 5, and fewer parameters allows you to go deeper as a result, and still have the same receptive field. So like it just, we got rid of like 5 by 5s when we said, oh, if we have two layers of 3 by 3, we have the same receptive field. Well, this is kind of going further and saying, yeah, you're right. We could even take that further and say, break my 3 by 3 into a 1 by n and an n by, or my 3 by 3 into a 1 by 3 and a 3 by 1. And yeah, so again, like this is how we do a 5 by 5 and have the same receptive field by 2 3 by 3s, and then we just kind of extend that further. So that's what inception V2 and V3 are. And then when you get to V4, that's when you add the residual connections in, and that's the network that with that one figure, it did the best. Yeah, you can see inception V3 gets all the way to 3.5 at the top right on using that competition. Okay.